Another example. Anyway, we'll take some example, but let's stop it at this point. For example, if you have a pole here, and the pole is cancelled by interconnection to a 0, and the pole and 0 are cancelled, so the pole is not observable here. Are you with me? There is a pole in this system, but the interconnection of this will give you a 0 also in y of t, y of s. So, the pole and 0 pole cancel, so that pole is not observable, which means state is not completely observable. So, isolated situations like this will occur in the interconnection of the system to make yt, which is the observable to you, which is the output which is observable to you. From this output, you will not be able to completely find out what is x of t. Question is, what are the conditions on this x of t? Or condition on this matrix, on this black box, and the condition, we have to condition on A or B, A and B, such that given y of t, I am able to find out x of t. And then I can apply control to modify this x of t. So, this is the observability problem. Then comes the controllability. What does controllability means? You will go back to your original state space representation. You are sitting at x t 0 and you want to move to some x of t, right. So, by giving some u of t, can we give a u of t? Are there some u of t which is applicable to this system such that this moves from here to here? If such input set is not available at all, not possible at all, and then you can't move it from here to here. What we said earlier is, given this and this, I can find this. Now, my question is, given this, I want this, is there any u of t which I can apply, so that the x t 0 moves to desired x of t, state control. So, this is second question, is it controllable? That means, are there UTs which will move x t 0 to desired x of t. First one is trying to find out whether the output yt, which is all that is available to me for measurement, I have measured y of t only. From this measurement, can I find out what is x of t uniquely? That is observability. And the controllability is, given the initial condition, are there any x of t's, u of t's, which will move this trajectory from here to here? So, these are the two questions which were raised by Kalman. Because unless these two are satisfied, there is no control problem, right? Like for example, we said in the networks, unless with the transfer function is realizable, there is no purpose in worrying about designing the network. So, we checked whether the given transfer function is possible to design a network for that. For that, some conditions have to be satisfied. Similarly, here is the unless the observability condition, controllability conditions are met, we will not be able to do a state control. So, Kalman raised this issue and found solution to this problem. Okay, let me go through this. This is a concept which you did not cover in 101. Let us take observability first. The issue is, if yt is given, is known for t greater than t0, can I find x of t? From the definition of state vector, we said, we are given the inputs and the initial state, x of t is uniquely defined, right. So, it is enough to know what is x of t0, because once x of t0 is known and inputs are known, I know x of t also. So, knowing x of t is as good as knowing x t0. So, the question is, given yt for t greater than 0, t0, can I find x t0 from that information? If x t0 is known, x of t can be found out by transition matrix. So, effectively the question is, given y of t, which is the measurable output, can I find x of t0? This is the observability problem. The answer is quite easy to analyze. We got observability matrix. Some symbol, and this matrix comes out to be C, CA, CA square, CAN minus 1. This matrix is known as the observability matrix, which has C here, C multiplied by A here, C multiplied by A square here, and so on. What is the size of this matrix? Remember what is our C? R by N, right? So, this matrix C is R by N. And how many such matrices are there? N of them. So, this vertical number of rows will be equal to NR by N. So, the matrix size is NR by N. If this matrix has a rank N, what does a rectangular matrix rank means? The rectangular matrix, right? Because number of rows are n bar, columns are n, the rectangular matrix. And what is the rank of a rectangular matrix? The largest size of P by P determinant, which is non-zero. That is the rank. So, what it says is, for this matrix, you should be able to find a sub matrix of size n by n, which is non-zero. Then this matrix is a rank n. So, this matrix here, which is size nr by n, must have a rank equal to n. If this is satisfied, then the system is observable. Proof of this is quite straightforward. Proof of this goes like this. Yt0 Cxt0, right? Y is equal to Cx plus du. Assume that the inputs are 0. We are only worrying about input xt0 moving. Then the first derivative of this will be equal to, according to the equation, C x first derivative t0, which is nothing but C a x t0 and go on doing this. That is n minus 1th derivative of this, evaluated t is equal to 0, comes out to be equal to C a n minus 1 x t 0. Right? All these are known, because yt is known. I can take derivative of yt and substitute at t is equal to t0. So, left hand side is all known, and right hand side is a matrix relation. This matrix multiplied by xt0, all of them have xt0. So, this matrix multiplied by xt0 is what we have on the right hand side, and we want xt0 to be uniquely defined, given yt0 all the derivatives. So, the solution will exist, non-zero solution will only exist when the rank of the matrix is equal to highest rank, which is n. So, that is the proof of this, saying that this matrix must have a rank equal to n. Because this side is all known, y is observed, yt is observed, I can take derivatives of that function and evaluate at t is equal to 0. These are known values, and these matrix values are also known. A is known, C is known. Only thing I do not know is xt0, what I am trying to find out, and xt0 can uniquely found out only when the matrix has a rank equal to n. So, that is the proof of this. Now, this matrix called observability matrix must have a rank equal to n. If it is not so, then given y of t, you will never be able to observe x of t. From there, you find out what is x of t, or equivalently x of t 0. And if you do not know the state, there is no question of controlling the state. So, you need to first know what is the state, initial state. So, that is the argument for which Kalman has developed. To before you do anything, you must check whether the system equation here given there consisting of C and A satisfy this condition or not, before you start saying that from the y of t I will be able to find out the state and then control the state. So, the first step. The second step is, okay, I have observed it, all right, then can I control it? Is there a set of UTs which uniquely will define the movement of the trajectory from x of t 0 to a desired value? Are there such inputs? and that is the controllability. The answer to this, I'll just write down the answer, and maybe sometime we will find out the I'm already lagging by one lecture. This matrix is called the controllability matrix. I know the double L is there or not. C. So, this matrix also must be of rank equal to n. This is also a rectangular matrix, and this size of that you can write down how much is the size of this. It becomes equal to, I don't know, symbols are same or not, but anyway you can write down what is the size of this. If this is satisfied, then you can find a set of UTs which will move x of t0 to desired value of x of t. So, this is known as the controllability matrix. So, before you do any control design, you will have to ensure that the system allows you to do observability, and also the system allows you to be controlled. If you cannot do that, no purpose in proceeding further.